Good evening, everyone. I am Jung Lee, the Vice President of EQS and Journal Club Manager of QISCA. It is my pleasure to introduce today's first speaker, Kyeongmyeong Jo from QIC. Kyeongmyeong Jo is currently a sophomore in the Department of Physics at Korea University. He has research experience in neutral atom cooling and trapping. Today he will be presenting a talk titled Many-body Physics on Rydberg Atom Quantum Simulator, sharing insights from the paper Probing Many-body Dynamics on a 51-atom quantum simulator, Bernien et al. Please join me in welcoming Kyeongmyeong Jo to the stage.
Thank you for the introduction. Can everyone hear me?
Yes.
All right. Thank you. Good evening, everyone. I hope you're having a good day. Today, I'll be presenting about the Rydberg atom quantum simulator and how we can prove many-body dynamics on it, such as quantum phase transition and quench dynamics. This is the brief overview of the presentation. So I'll talk about the basic techniques of laser cooling and how you can make an array of atoms using optical devices. And lastly, I'll go over how the Looking group at Harvard managed to probe many-body dynamics with a Rydberg atom quantum simulator. But before we get into anything else, we first have to know what a quantum simulator is. A quantum simulator is a controllable quantum system that mimics the behavior of another less accessible quantum system. And this idea arises from a fundamental challenge in physics, which is simulating many-body quantum systems. When particles interact in highly entangled ways, the number of quantum states grows exponentially with the system size, which makes the classical simulation practically impossible. And the quantum simulators bypass this limitation by directly implementing the target quantum Hamiltonian in a physical platform of your choice. And these simulators allow us to study complex quantum phenomena like quantum phase transitions in a highly tunable and controlled environment, which is why Feynman famously said, nature isn't classical, and if you want to make a simulation of nature, you'd better make it quantum mechanical. And this just encaptures the basic idea of quantum simulator. So like I've mentioned, we need a platform for quantum simulators, and we'll use something called the Rydberg atom. Rydberg atoms are atoms that are excited to energy states with high principal quantum number. And atoms in such states are called Rydberg states. And the table below shows the scaling properties of the Rydberg atoms for principal quantum number of 50. Some notable physical properties are the orbital radius of a Rydberg atom scales as n squared, meaning that the electron can be hundreds of nanometers away from the nucleus. And this large size of the atom makes Rydberg atoms easy to manipulate with external fields, and it enables precise spatial control. And their radiative lifetime scales as n to the power of 3, reaching hundreds of microseconds for a high principal quantum number. And this extended coherence time allows for long controlled quantum operations, making Rydberg atoms reliable for experiments on quantum information processing. And the dipole moment between the adjacent Rydberg states scales as n squared because the electron and the nucleus are so far apart from each other, leading to strong long-range interactions between atoms. And these strengths and tunability of interactions are key to simulating quantum many-body systems with long-range correlations that are difficult to realize in other quantum platforms. And this Rydberg atom has a special property called the Rydberg blockade mechanism. And it simply states that if two atoms are separated with the distance smaller than the blockade radius defined here, only one atom can be excited to the Rydberg state. And this is because the interaction between the Rydberg atoms can be approximated as the dipole-dipole interaction, which leads to the energy shift being proportional to the r to the power of -6, where r is the separation distance between the atoms. And this implies that the energy shift diverges at r values close to 0, as you can see in this graph. And as a result, the presence of a Rydberg atom can prohibit the neighboring ground state atom from becoming Rydberg atoms. And the simultaneous creation of Rydberg atoms within this lock gate radius distance results in quantum mechanically entangled states, defined as psi plus here. And how would we control individual atoms? So to make a Rydberg atom, to like control individual Rydberg atom, you need to like have a precise control over like one atom, right? And to do experiments with atoms in room temperature, you need to cool the atoms to microkelvin temperature. And to do this, you use a technique called magneto-optical trap. And what this is basically is that you propagate 6 lasers and you produce a magnetic field with the anti-Helmholtz coil. You need 2 lasers for each degree of freedom to compensate for the Doppler shift in the atom's reference frame. And this magnetic field by the coil causes the splitting of energy level delta, delta E, shown here, which is also known as the Zeeman effect. And following the selection rules associated with the magnetic quantum number MF and the polarization of light, you can use the red detuned lasers to that are circularly polarized, as shown here, to access the shifted energy levels and effectively cool the atoms. So mathematically, the force that atoms experience due to all these effects can be written like this, where alpha and beta are constants. So what you can deduce here is that you have a position dependent, so z dependent, and velocity dependent damping force on the atom, which allows you to trap a cloud of atoms in the center of the trap here, where the magnetic field is 0. And with that with that cloud of atoms, we want to trap the atoms onto a laser called optical tweezers. And later in the experiment, these tweezers will be moved dynamically so that if there is an atom in the tweezer, the atoms can be controlled individually. And this is also known as the optical dipole trap. So how this works is the dipole potential under the classical limit can be written like this in electrodynamics. And the factor of 1/2 just indicates that the dipole is induced. And by finding the expression for polarizability alpha from the Lorentz oscillator model and under the rotating wave approximation, which where you just remove the highly oscillating terms in the denominator, we get the following expression for the dipole potential. And recall that if there is an oscillating electric field interacting with the atom, the energy level of the atom shifts by a certain amount, and this is called the AC Stark shift. So under the presence of oscillating electric field, the energy levels, it gets shifted by a certain amount. And in the 2-level system, we find that the AC Stark shift can be expressed as follows. And notice how the 2 expressions are equal. The optically induced AC Stark shift of the ground state exactly corresponds to the dipole potential for the 2-level atom. So what this means is that we can manipulate the intensity of the tweezer laser to change the depth of the potential level and trap atoms in the ground state. So the higher intensity, the better for trapping. And we want to load single atoms in the optical tweezer instead of several atoms. And we can make use of so-called collisional blockade mechanism to control the number of atoms in the tweezer. So if you look on the left, this is the blue graph is the fluorescence signal showing sub-Poissonian statistics, which deviates from the expected Poissonian statistics from a normal fluorescence signal, which is, I think it's the green graph. So you see there's a missing peak here, right? And this leads to the blue graph showing sub-Poissonian statistics. And this happens because if you make the beam waist, so the size of the tweezer cross-section at some focal point you want to trap atoms at, if you make it small enough, atoms will get caught in the trap and they will collide inelastically until there are 0 or 1 atom left in the tweezer. If you look at the diagram on the right, the W0 term is the beam waist. And if you make it small enough, so in this case, if you make it under 1 micrometer, you can see that it kind of forms a plateau where you have a constant average number of atoms over multiple magnitudes of loading rate around at a value of 0.5, 0.6. And this tells you that the probability of single atom loading is 50%. We now like to make an array of tweezers because we can't do anything with one atom. We need to have like a system of atoms so that we can exploit the Rydberg blockade mechanism on it to study quantum properties. And this can be done using optical device called SLM, which stands for spatial light modulator. And what this does basically is that it has liquid crystals in it that are birefringent. So applying a voltage to the liquid crystal cell changes the effective refractive index seen by the incident wave, which means that we can change the phase of the incident beam. And in this case, that would be the optical tweezer beam. However, it's not the phase that we wish to change on the image plane, but rather the amplitude, because we want to kind of designate our own amplitude map. What I mean by this is that, for instance, we want a amplitude of 1 in places we want the tweezer to be and 0 everywhere else. And to achieve this, we use something called the GS algorithm. And how the algorithm works is represented on this block diagram on the right. We choose a random initial phase map and perform a fast Fourier transform to the image plane. And there, you keep the phase, the transformed phase, and you replace the amplitude with the target amplitude. And if the amplitude converges to the target amplitude in this step, you stop the algorithm. Otherwise, you perform inverse Fourier transform back to the SLM plane, and you keep the phase. You update the phase, sorry. You update the phase, and you replace the amplitude to the initial amplitude with the updated phase. And you do this iteration until you get the desired intensity. And you can kind of make any arbitrary arrays of your requirement. And so consider like 1D chain of atoms in the optical tweezer. We first need to get some intuitive understanding of the Hamiltonian used in the many-body physics. And as we have atoms lined up in a one-dimensional array in this case, we can think of the interaction as the 1D Ising model. And based on this analogy, the Rydberg atom Hamiltonian closely resembles the Ising model with long-range interactions and a tunable external field. So the first term is the coherent driving term, and it represents the interactions, the coupling between the ground state and the Rydberg state at some site I. Large omega here is the Rabi frequency, defined as the electric field strength times the transition dipole moment between psi 1 and psi 2 divided by h bar. So it's the frequency at which the probability amplitude of two atomic energy levels fluctuate in an oscillating electromagnetic field. The second term is the detuning term, and this term describes how far the laser frequency is detuned from the natural transition frequency of the atom. And the parameter delta, that's the energy difference between the Rydberg state and the ground state relative to the laser's frequency. And since the number operator Ni equals 1 if the atom is in the Rydberg state and 0 if the atom is in the ground state, this term basically shifts the energy of the Rydberg state by a factor of negative delta. The last term is the interaction term. This term accounts for the interactions between the atoms in the Rydberg state, and it decays with the distance x between atoms as x to the power of -6, which is the characteristic feature of dipole-dipole interactions. And when two atoms are close enough, the interaction energy Bij becomes so large that it prevents both atoms from being excited simultaneously because, say, both atoms are at site, both atoms at site I and J are Rydberg states, then this interaction term will survive and will contribute to the Hamiltonian, which is energetically unfavorable. And this shows that the Hamiltonian effectively reflects upon the blockade mechanism. Now, with this Hamiltonian, we can experimentally implement the quantum simulator on the chain of Rydberg atoms. So individual rubidium atoms are trapped using the optical tweezers, which are the red vertical beams, and they're arranged into defect-free arrays by some assignment algorithm. The coherent interactions between the coherent interactions Vij between the atoms, which are the arrows you see here, are enabled by exciting them to Rydberg state using horizontal blue and red beams with strength omega and detuning delta. If you look at this figure, the two-photon transition couples the ground state to the Rydberg state via an intermediate state E. The blue laser has a detuning of a small delta, and the lasers are circularly polarized with wavelengths 420 nanometers and 1013 nanometers, and they have a single photon Rabi frequencies of omega B and omega R. And notice how the value of small delta is far greater than the values of single photon Rabi frequencies. And this is to suppress the population in the intermediate state. If the detuning delta is too small compared to these two terms, a significant fraction of population will temporarily occupy the intermediate state, and it will cause a spontaneous emission because it can decay back to the ground state or other, unwanted states, which introduces some decoherence to the system. And furthermore, with large detuning, the two-photon transition between the ground state and the Rydberg state becomes effectively coherent, and the system behaves like a simple two-level system. And by making the blue laser non-resonant to the intermediate state, simplifies the transition to the two-level system with the effective Rabi frequency of omega B, omega R over 2 delta. And as for the experiment protocol, it consists of loading atoms into a tweezer array and rearranging them into a desired configuration. And after this, the system evolves under some unitary evolution with tunable parameters delta, omega, and the interaction strength. Then after some time, we detect the final state using fluorescence imaging. Atoms in the ground state remain trapped whereas atoms in the Rydberg state are ejected from the trap and detected as the absence of fluorescence because the electron of the Rydberg atom is so far away from the nucleus, and this results in high polarizability. So when Rydberg atom interacts with the external light field from the optical tweezer, it experiences a repulsive potential and gets anti-trapped in the tweezer. And figure D just confirms the coherence of the system by checking the square root of n scaling of Rabi frequency, where n is the number of atoms entangled. So if you say, if you let the Rabi frequency of this system be omega, the Rabi frequency of this system would be square root 2 times omega. This system is would be square root of 3 times omega because 3 atoms are entangled. And as mentioned earlier, the Hamiltonian that describes the Rydberg interaction resembles the Ising model for effective spin 1/2 particles with variable interaction range. And this and its ground state exhibits different types of many-body phases that break distinct spatial symmetries. And so what I mean by this is that at large negative ratio of delta over omega here, the ground state corresponds to the disordered paramagnetic phase where all atoms in the ground state. However, when you increase this detuning term to a large positive value, the number of Rydberg atoms increase and the interaction between the excited atoms is no longer negligible. So if you look at the Hamiltonian, what this means is that the number operator term, the number operator coefficient delta would outweigh the Rabi frequency in the coupling term. And these interactions generate spatially ordered phases called Rydberg crystals with different spatial symmetries depending on the interaction range. For example, if the atom experiences blockade for neighboring atoms, so Vi, I plus 1, but has negligible interaction between the next nearest neighbor, so this term is negligible, then the ground state corresponds to the Rydberg crystal with Z2 order state in a manner analogous to antiferromagnetic order in magnetic systems. So Z2 order state is basically the repetition of GRGR or RGRG and so on. And we change the interaction strength by change the trap spacing A and observe the Z3 and Z4 ordered state in a very similar manner. And you can see the fluorescence image of different order states due to different trap spacing when you adiabatically change the detuning. And we can compare how the quantum phase transition on a quantum simulator changes with respect to the system size. So the diagram on the left shows the 7-atom system. The top figure is basically describing how the system was controlled under laser parameters. So you turn on the Rydberg laser, which is represented in the blue graph. And then you slowly change the detuning term adiabatically in a timescale of a few microseconds, I think, across the critical point of phase transition. And the results are presented below. So here, we're looking at the Rydberg probability of individual atoms. So the reddish and greenish graphs in the middle, these represent atoms that are excited to the Rydberg state. And if you look at the index here, it corresponds to 1, 3, 5, and 7, which just represents the Z2 ordered state. And at the bottom graph, it shows that as you change the stop time, you have all the atoms at the ground state first. And if detuning value crosses the critical point, all the other states are suppressed by the blockade interaction. And the most probable state is the state that exhibits the Z2 order. So RG, RG, R, GR. Yes, this state. And this is also the case when you increase the size of the system up to 51 atoms. When you increase the system size, the Hilbert space dimension increases exponentially. But you can see that the most frequently occurring state is the perfectly Z2 order state with probability of around 1%, which is remarkable considering the large dimension of the Hilbert space. And so in the 51 atom quantum simulator, when you change the detuning ratio from negative to positive, you observe an ordered pattern of atoms alternating between the ground state and the Rydberg state. But this pattern does not continue along the entire 51 atom chain. Many ordered domains are seen in the single shot fluorescence images in the top figure. So what I mean by ordered states is the pair of ground state and Rydberg state. So this is an ordered state. This is ordered domain. Sorry, ordered domain. This is an ordered domain. But these domains are separated by domain walls that consist of two neighboring atoms in the same electronic state, either ground or Rydberg. So this is the domain wall of ground, and this is the domain wall for Rydberg state. And therefore, the number of domain walls in the 51 atom system can be considered as a quantification of the transition from the disordered phase at the top to the ordered Z2 phase as a function of detuning. So in the negative detuning regime, in this graph, the domain wall density is high as all the atoms are in the ground state. So it basically equal 1. And as the system enters the Z2 phase, and the number of domain walls decrease, and while the mean number of domain walls decrease as the detuning is increased adiabatically, the decrease is not consistent. So the variance of the domain wall density, it peaks at the transition point of the quantum phase transition. And the variance peak at the transition point is in agreement with expectations for Ising type second order, so continuous quantum phase transition. And another important value to note is that the phase transition occurs at a non-zero value of the detuning term. And this is because in a finite size system, so we don't have like infinite length of Rydberg atom chain. We have a 51 atom chain. So what we have here is a finite size system, and the energy gap between the ground state and the first excited state, it closes at a slightly larger value of detuning compared to an infinite system. And this is because the correlation length is finite. In an infinite system, so in like ideal system, the correlation length diverges at the critical point where the phase transition occurs, resulting in like a complete closing of the energy gap at some critical value of detuning. And this case would be delta equals 0. But for a finite system like we have here, the correlation length is limited by the size n. So the system requires a larger detuning to reach the same level of critical fluctuations. And this results in the critical point appearing some value that's larger than the critical value of the detuning. And beyond exploring quantum phase transitions, the quantum simulator further enables us to study the many body dynamics that are far from equilibrium, and they're called quench dynamics. A quench is a process where a system composed of many interacting particles undergo a sudden significant change in its parameter. So basically, you want to disrupt the system's equilibrium state by rapidly changing a parameter within the system, which leads to complex non-equilibrium dynamics. So here, they investigated the quench dynamics of the Rydberg crystal initially prepared in the Z2 ordered state. So if you look at the fluorescence signal, this corresponds to think nine atom system displaying the Z2 ordered state. And then with this state, you change the detuning term. So you change the detuning term rapidly to the single atom resonance at delta equals 0. And after the quench, we observe oscillations between the initial crystal here and its complementary crystal in the fluorescence signal, which means that every atomic state in each position is inverted. This is well represented by histogram. So if you have RG, 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 after the quench, we have GR, 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 and after some time, we go back to RG, RG, RG. And these oscillations are observed to be robust and persist, and they persist over several periods with the frequency independent of the system size. So the frequency is almost the same for 9 atoms and 51 atoms. These oscillations are measured by the domain world density function over time. And the domain world density oscillation is at minimum when the system is in the perfectly Z2 ordered state, and maximum when the system has flipped to its complementary state. And this phenomenon is known as the quantum many-body scar. It was not known when this paper was published, so this paper was published in 2017, so this kind of chaotic behavior is very recent. And it requires a very deep mathematical explanation, so I will just briefly go over what it is in the conclusion, which is the next slide. Okay. So to conclude, we observed phase transitions into spatially ordered state that break various discrete symmetries by changing the detuning parameter and the interaction range. We also verified the high fidelity preparation of these different phase states, and we further investigated the dynamics across the phase transition in large arrays of atoms. And with this quantum simulator in hand, we can further investigate a mechanism called quantum Kibble-Zurek mechanism, which predicts the number of domain walls with system size and sweep rate of the detuning term. And furthermore, the quantum many-body scar I mentioned earlier is also a new field of study. So basically, quantum many-body scars are non-thermalizing states, so they don't they tend to not go back to equilibrium in quantum systems that exhibit long-lived coherent oscillations instead of relaxing to a thermal equilibrium. And this is what we observed earlier. And unlike most states in chaotic many-body systems that lose memory of their initial conditions and behave, kind of thermally, these scarred states retain some structure and they show periodic dynamics over time. And these states defy typical behavior predicted by previous theories, and they provide new insights into non-equilibrium quantum dynamics. This is it for my presentation, and thank you for listening, and any questions would be appreciated. Thank you.